So welcome back. We are going to go through the DOE Fundamental Handbook, Volume 2 of Thermodynamics, Heat Transfer, and Fluid Flow. So this volume 2, the keywords again is thermodynamics, heat flow, fluid flow, and also Bernoulli's equation. The thermodynamics, heat transfer, and fluid flow handbook has 3 modules. The first module, we talked about thermodynamics. In this module, we cover properties of fluids and how these properties affect various processes. It also explained how energy balances can be performed on facility systems or components and how efficiency can be calculated. In volume 2, we're going to talk about heat transfer. And this model, we're going to look at conduction, convection, and radiation heat transfer. And also this module explains how specific parameters affect the rate of heat transfer. So given the operating conditions, so these are some of the objectives, given the operating conditions of a thermodynamic system and the necessary formulas, we're going to evaluate the heat transfer processes which are occurring. The enabling objectives, we're going to describe the difference between heat and temperature. We're going to describe the difference between heat and work. We're going to describe the second law of thermodynamics and how it relates to heat transfer. We're going to describe the 3 modes of heat transfer and define the following terms as they relate to heat transfer, such as heat flux, thermal conductivity, long mean temperature difference, convective heat transfer coefficient, overall heat transfer coefficient, and bulk temperature. Given Fourier's law of conduction, we're going to calculate the conduction heat flux in a rectangular coordinate system. We're going to, given a formula and necessary values, calculate the equivalent thermal resistance. Given Fourier's law of conduction, we're going to calculate the conduction heat flux in a cylindrical coordinate system. Given a formula for heat transfer and the operating conditions of a system, we're going to calculate the rate of heat transfer by convection. And then we're going to describe how the following terms relate to radiant heat transfer, and that's black body radiation, emissivity, radiation configuration factor. Then we're going to describe the difference between the temperature profiles for counterflow and parallel flow heat exchangers. We're going to describe the difference between regenerative and non-regenerative heat exchangers. Given temperature changes across heat exchanger, we're going to calculate the log mean temperature difference for the heat exchanger, and then given formulas for calculating the conduction and convection heat transfer coefficients, we're going to calculate the overall heat transfer coefficient of a system and describe the processes that occur in the following regions of the boiling heat transfer curve, such as nuclear boiling, partial film boiling, departure from nuclear boiling or D&B, and then critical heat flux. And then given the operating conditions for a typical nuclear reactor, we're going to describe the heat transfer processes that are occurring. We're going to describe the power generation process in a nuclear reactor core and the factors that affect power generation. We're going to describe the relationship between temperature, flow, power during the operation of a nuclear reactor. We're going to define nuclear enthalpy, rise hot channel factor, average linear power density, nuclear heat flux hot channel factor, and then heat generation rate of a core, and then volumetric thermal source strength. We're going to calculate the average linear power density for an average reactor core fuel rod, describe a typical reactor core axial and radial flux profile, describe the typical reactor core fuel rod axial and radial temperature profile, define the term decay heat, and then given the operating conditions of a reactor and the necessary formulas, we're going to calculate the core decay heat generation, and we're going to describe 2 categories for removing decay heat from a reactor core. And so in this first transfer, we're going to talk about heat transfer terminology. In order to understand and communicate in the thermal science field, certain terms and expressions must be learned in heat transfer. So the enabling objectives for this chapter is to describe the difference between heat and temperature, describe the difference between heat and work, describe the second law of thermodynamics and how it relates to heat transfer, describe the 3 modes of heat transfer, and then define the following terms as they relate to heat transfer, such as heat flux, thermal conductivity, log mean temperature difference, convective heat transfer coefficient, overall heat transfer coefficient, and bulk temperature. So the first is to talk about heat and temperature. In describing heat transfer problems, the students, they often mistake the interchangeability using the 2 terms heat and temperature, but actually there's a distinct difference between the 2. Okay. Temperature is a measure of the amount of energy possessed by molecules of a substance, and is relative measure of how hot and cold a substance is, and it can be used to predict the direction of heat transfer. The symbol for temperature is T, and the common scales used for measuring temperature are Fahrenheit, Rankine, Celsius, and Kelvin scales. Heat is energy in transit. The transfer of energy as heat occurs at the molecular level as a result of a temperature difference. So heat is capable of being transmitted through solids and fluids by conduction, through fluids by convection, and through empty space by radiation. The symbol for heat is Q. And common units for measuring heat are the British thermal unit, or BTU, in the English system of units, and the calorie in the SI system, or international system of units. Also, you need to make the distinction between heat and work. The distinction should also be made between these 2. They both represent energy in transition. Work is the transfer of energy resulting from the force acting through a distance, and heat is energy transferred as a result of a temperature difference. Neither heat nor work are thermodynamic properties of a system. Heat can be transferred into or out of a system, and work can be done on or by a system, but a system cannot contain or store heat or work. Heat into a system and work out of a system are considered positive quantities. So when a temperature difference exists across the boundary, the second law of thermodynamics indicates the natural flow of energy is from the hotter to the colder body. And the second law of thermodynamics denies the possibility of ever completely converting into work all of the heat that's supplied to a system in a cycle. The second law of thermodynamics, described by Planck in 1903, states that it is impossible to construct an engine that will work in a complete cycle and produce no other effect except the rising of a weight and the cooling of a reservoir. So the second law says that if you draw heat from a reservoir to raise the weight, lowering the weight will not generate enough heat to return the reservoir to its original temperature, and eventually the cycle will stop. So if two blocks of metal at different temperatures are thermally insulated from their surroundings and are brought into contact with each other, the heat will flow from the hotter to the colder. Eventually, the two blocks, they'll reach the same temperature and the heat transfer will cease. And so energy has not been lost, but instead some energy has been transferred from one block to another. So what are the modes of transferring heat? Heat is always transferred when a temperature difference exists between two bodies. There are three basic modes of heat transfer. That's conduction, convection, and radiation, where conduction involves the heat transfer of heat by the interactions of atoms or molecules of a material through which the heat is being transferred. Convection involves the transfer of heat by mixing and motion of macroscopic portions of a fluid, and radiation is radiant heat transfer, and it involves the transfer of heat by electromagnetic radiation that arises due to the temperature of a body. So these three modes of heat transfer are discussed in greater detail in the subsequent chapters in this particular module. So heat flux is the rate in which heat is transferred, and is represented by the symbol Q. Common units for heat transfer are BTU per hour. And sometimes it's important to determine the heat transfer rate per unit area, or the heat flux, in which the symbol Q is used. And so units of heat flux are BTU per hour foot squared. And the heat flux can be determined by dividing heat transfer rate by the area through which the heat is being transferred. And so the formula is Q, where heat flux is equal to Q, heat transfer divided by A, the area. So the first Q is heat flux, that's in BTU per hour foot squared. The other Q on the other side of the equation is the heat transfer rate, and that is BTU per hour. Remember, a rate is anything divided by a unit of time. And then area is in foot squared. Thermal conductivity is heat transfer characteristics of a solid, which are measured by a property called thermal conductivity. K is measured in BTU per hour foot degree Fahrenheit, and it's a measure of the substance's ability to transfer heat through a solid by conduction. And the thermal conductivity of most liquids and solids varies with the temperature. So for vapors, it depends on the pressure. The log mean temperature difference in a heat exchanger, the inlet and outlet temperatures are commonly specified based on the fluid that's in the tubes. The temperature change that takes place across the heat exchanger from the entrance to the exit is not linear. A precise temperature change between two fluids across a heat exchanger is best represented by the log mean temperature difference, LMTD, or delta T sub LM. And so that is defined, and in the equation below is delta T LM is equal to delta T2 minus delta T1 over the natural log of delta T2 divided by delta T1. Okay. And remember, delta is final minus initial. So delta T2 is the larger temperature difference between the two fluid streams at either the entrance or exit of the heat exchanger. Delta T1 is the smaller temperature difference between the two fluid streams at either the entrance or the exit of the heat exchanger. Convective heat transfer coefficient. The convective heat transfer coefficient H defines in part heat transfer due to convection. The convective heat transfer coefficient is sometimes referred to as the film coefficient, and it represents the thermal resistance of a relatively stagnant layer of fluid between a heat transfer surface and a fluid medium. And the common units for convective heat transfer coefficient is BTU per hour foot square degree Fahrenheit. Overall heat transfer coefficient, in the case of combined heat transfer, is common practice to relate the total rate of heat transfer, which is Q, the overall cross-sectional area of heat transfer, which is A sub 0, and the overall temperature difference, which is delta T sub 0, using the overall heat transfer coefficient U sub 0. The overall heat transfer coefficient combines the heat transfer coefficient of the two exchanger fluids and the thermal conductivity of the heat exchanger tube. So U sub 0 is specific to the heat exchanger and the fluids that are used in the heat exchanger, where Q is equal to U sub 0, A sub 0, and delta T sub 0. Okay. Where Q is the rate of heat transfer, BTU per hour. U is the overall heat coefficient in BTU per hour foot square degree Fahrenheit. And A is the cross-sectional area of heat transfer. And delta T is the overall temperature difference in degrees Fahrenheit. Bulk temperature, the fluid temperature, T sub B, is referred to as the bulk temperature. And this varies according to details of the situation. The flow adjacent to the hot or cold surface, T sub B, is the temperature of the fluid that is far from the surface, for instance, the center of the flow channel. So for boiling or condensation, TB is equal to the saturation temperature. TB is equal to the saturation temperature. So I'll give you a few moments to notate any equations. So in this next chapter, they talk about conduction heat transfer. And this is the transfer of thermal energy by interactions between adjacent atoms and molecules in the solid. So the enabling objectives is given Fourier's law of conduction, calculate the conduction heat flux in a rectangular coordinate system. Given the formula and the necessary values, calculate the equivalent thermal resistance, and given Fourier's law of conduction, calculate the conduction heat flux in a cylindrical coordinate system. So conduction involves transfer of heat by the interaction between adjacent molecules in the material. Heat transfer by conduction is dependent upon the driving force of temperature difference and the resistance to heat transfer. The resistance to heat transfer is dependent upon the nature and the dimensions of heat transfer in the medium. And all heat transfer problems involve a temperature difference, the geometry, and physical properties of the object that's being studied. In conduction heat transfer problems, the object being studied is usually a solid. So convection problems involve a fluid medium. Radiant heat transfer problems involve either solid or fluid surfaces separated by a gas, vapor, or a vacuum. And there are several ways to correlate the geometry, physical properties, and the temperature difference of an object with the rate of heat transfer through the object. In conduction heat transfer, the most common means of correlation is through Fourier's law of conduction. And this law in equation form is used most often in its rectangular or cylindrical form, i.e. pipes and cylinders. Okay, both of which are represented by the equations below. So for these rectangular forms, Q is equal to K, A times delta T over delta X. In cylindrical form, Q is equal to K, A times delta T over delta R. Where Q is the rate of transfer in BTU per hour, A is the cross-sectional area of heat transfer in feet squared. Delta X is the thickness of the slab in feet. Delta R is the thickness of the cylindrical wall in feet. And delta T is the temperature difference in degrees Fahrenheit. And K is the thermal conductivity of a slab, and that's in BTU per feet hour degree Fahrenheit. So to use those equations, we use those equations in determining the amount of heat transfer by conduction, and it's given by these following examples. So if we calculate conduction through rectangular coordinates, the question that is asked is 1,000 BTU per hour is conducted through a section of insulating materials shown in figure 1. It measures 1 foot squared in cross-sectional area. The thickness is 1 inch, and the thermal conductivity is 0.12 BTU per hour foot degree Fahrenheit. And they ask you to compute the temperature difference across the material. So they use the equation 2,4 that Q is equal to K A times delta T over X, and they solve for delta T because you're looking for the temperature difference. Okay, so they get delta T by itself because you're looking for the temperature difference. So delta T, the equation that you finally use, is delta T is equal to Q times delta X over Ka. Okay, and so they plug in and solve. So 1,000 BTU per hour times 1 over 12 feet divided by 0.12 BTU per hour foot degree Fahrenheit times 1 foot squared, and you come up with a temperature difference or delta T of 694 degrees Fahrenheit. Then in the second example, you have a concrete floor with conductivity of 0.8 BTU per hour foot degree Fahrenheit, and it measures 30 feet by 40 feet with a thickness of 4 inches. And the floor has a surface temperature of 70 degrees Fahrenheit, and the temperature beneath is 60 degrees Fahrenheit. And they ask you what is the heat flux and the heat transfer rate through the floor. So they use the equations 2,1 and 2,4. So Q is equal to Q over A, which is equal to K over delta T divided by delta X. then they plug in and solve. So 0.8 BTU per hour foot degree Fahrenheit times 10 degrees Fahrenheit over 0.333 feet is equal to 24 BTU per hour foot squared. And then they use the equation Q is equal to KA times delta T over delta X is equal to Q times A. And so they multiplied 24 BTU hour per foot squared times 1,200 feet squared, and they come up with a Q of 28,800 BTU per hour. And so for the next section, they talk about equivalent resistance method, and they let you know it's possible to compare heat transfer to current flow in electrical circuits. The heat transfer rate may be considered as a current flow, and the combination of thermal conductivity, thickness of the material, and area as a resistance to the flow. And so the temperature difference is the potential or driving function for heat flow, and resulting in a Fourier equation being written in a form similar to Ohm's law of electrical circuit theories. And if thermal resistance term delta X over K is written as a resistance term, where resistance is the reciprocal of thermal conductivity divided by the thickness of the material, the result is the conduction equation being analogous to electrical systems or networks. And so the electrical analogy may be used to solve complex problems involving series and parallel thermal resistances. So in figure 2, they show the equivalent resistance circuit. And the typical conduction problem in its analogous electrical form is given by the following example, where electrical Fourier equation is written as Q is equal to delta T over R, so TH, where Q is heat flux, okay, and that's represented by Q over A, and the units are BTU per hour foot squared. Delta T is the temperature difference, and that's in degrees Fahrenheit. RT, so TH is your thermal resistance. That's the same as delta X over K, and the units are hour foot squared degree Fahrenheit per BTU. So they have you do a calculation for this electrical analogy between electrical flow and heat transfer. So they ask the question, a composite protective wall is formed of a 1-inch copper plate, a 1/8 inch layer of asbestos, and a 2-inch layer of fiberglass. The thermal conductivities of the materials in the units are in BTU per hour foot degree Fahrenheit are as follows. K for copper is 240. K for asbestos is 0.048. And K for fiberglass is 0.022. The overall temperature difference across the wall is 500 degrees Fahrenheit, and they ask you to calculate the thermal resistance of each layer of the wall and the heat transfer rate per unit area, which is the heat flux through the composite structure. So what you see is that they they have the equations for resistance for each of the different components. So R of copper is equal to the delta X of copper over the K of copper. R of the asbestos is equal to delta X of the asbestos over the K of asbestos. And R of fiberglass is equal to delta X of fiberglass over the K of fiberglass. And then they go in and they put in the conversion factors. So 1 inch is equal to 1 inch times there being 12 inches in a foot. They've rearranged this conversion factor. So 1 inch times 1 foot over 12 inches divided by 240 BTU per hour foot degree Fahrenheit. For the R for copper is 0.000 or 0.000347 hour feet squared degree Fahrenheit per BTU. For asbestos, they have 0.125 inches times that conversion factor, 1 foot over 12 inches divided by that K, which is 0.048 BTU per hour foot degree Fahrenheit. And so that R for asbestos is 0.2170 hour foot square degree Fahrenheit per BTU. And for fiberglass, 2 inches. And they multiply times the conversion factor times 1 foot over 12 inches divided by that K, which is 0.022 BTU per hour foot degree Fahrenheit. And that R is 7.5758 hour foot squared degree Fahrenheit per BTU. And so Q over A is equal to TI minus T0 divided by those R's that were previously calculated. So the sum of R for copper, R for asbestos, R for fiberglass. So they plug in 500 degrees Fahrenheit divided by 0.00347, 0.2170, and 7.5758, and they just indicate the units outside of the parentheses because they all have the same units. And so that Q over A simplifies to 64.2 BTU per hour foot squared. Okay, that's how they work it out. Conduction for cylindrical coordinates. This is heat transfer across a rectangular solid, and it's the most direct application of Fourier's law. Heat transfer across a pipe or heat exchanger tube wall is more complicated to evaluate. So across a cylindrical wall, the heat transfer surface area is continually increasing or decreasing. And so in figure A, you see a cross-sectional view of a pipe constructed of a homogeneous material. The surface area for transferring heat through a pipe, neglecting the ends, is directly proportional to the radius of the pipe and the length of the pipe, where A is equal to 2 pi RL. As the radius increases from the inner wall to the outer wall, the heat transfer area increases. The development of an equation evaluating heat transfer through an object with cylindrical geometry begins with Fourier's law equation, where Q is equal to K times A times delta T over delta R. And from the discussion, it is seen that no simple expression for area is accurate. Neither area of the inner surface nor the area of the outer surface alone can be used in the equation. And for a problem involving cylindrical geometry, it's necessary to define the log mean cross-sectional area. Okay, so they're having to log transform the cross-sectional area. So A sub LM is equal to A outer minus A inner divided by the natural log of A outer over A inner. So substituting the expression for 2 pi RL for the area, equation 2.7 allows the log mean area to be calculated for the inner and outer radius without calculating the inner and outer area. So A sub LM is equal to 2 pi R outer L minus 2 pi R inner L divided by the natural log of 2 pi R outer L over 2 pi R inner L. And this is reduced to 2 pi R L times R outer minus R inner over the natural log of R outer over R inner. Okay, so they took out a common factor for this last equation. Okay, they took out a common factor for this last equation. So this expression for log mean area is inserted back into equation 2.5 and it allows you to calculate heat transfer for cylindrical geometries. So they're showing you how they've gone back and substituted in for this particular equation. So Q is equal to KLM delta T over R. They've substituted for ALM. And they've gotten K is equal to 2 pi L R0 or R outer minus RI or R inner over the natural log of R outer over R inner times the temperature outer minus temperature inner over R outer minus R inner. So L is the length of the pipe in feet. RI is the inside pipe radius in feet, and RO is the outside pipe radius in feet. And so an example problem is a stainless steel pipe with a length of 35 feet, has an inner diameter of 0.92 feet and an outer diameter of 1.08 feet. The temperature of the outer surface of the pipe is 122 degrees Fahrenheit, and the temperature of the outer surface is 118 degrees Fahrenheit. So the thermal conductivity of the stainless steel is 108 BTU per hour foot degree Fahrenheit, and they ask you to calculate the heat transfer rate through the pipe and to calculate the heat flux at the outer surface of the pipe. So they go through and solve the problem. Q is equal to 2 pi KL T sub H minus T sub C divided by the natural log of R O over RI. And then they plug in and solve. So 6.28 times 108 BTU per hour foot degree Fahrenheit times 35 feet times 122 minus 118 degrees Fahrenheit divided by the natural log of 0.54 over 0.56. And they solve to get a Q of 5.92 times 10 to the 5th BTU per hour. And then Q is equal to Q over A. They substitute in for A, so Q is equal to 2 pi R outer L. So 5.92 times 10 to the 5th BTU per hour divided by 2 times pi, which is 3.14 times 0.54 feet times 35 feet gives you a Q of 4,985 BTU per hour foot squared. And then the next example is you have a 10-foot length pipe with an inner radius of 1 inch, an outer radius of 1.25 inches, and it has an outer surface temperature of 250 degrees Fahrenheit. The heat transfer rate is 30,000 BTU per hour, and you have to find the interior surface temperature, assuming that K is 25 BTU per hour foot degree Fahrenheit. So they use the equation Q is equal to 2 pi KL times TH minus CC divided by the natural log of RO divided by RI. They solve for TH, so TH is equal to Q natural log R O over RI divided by 2 pi KL plus TC, and then they plug it and solve. So 30,000 BTU per hour times the natural log of 1.25 inches over 1 inch divided by 2 times pi, which is 3.14 times 25 BTU, hour foot BTU per hour foot degree Fahrenheit times 10 feet gives you a TH of 254 degrees Fahrenheit. And so the evaluation of heat transfer through a cylindrical wall can be extended to include the composite body composed of several concentric cylindrical layers, is shown in the figure below. So let's stop. So the next problem, they asked the question, a thick wall nuclear coolant pipe with a KS of 12.5 BTU per hour foot degree Fahrenheit with 10 inches inside diameter and 12 inches outside diameter is covered with a 3-inch layer of asbestos insulation. Ka is 0.14 BTU per hour foot degree Fahrenheit. And if the inside wall temperature of the pipe is maintained at 550 degrees Fahrenheit, calculate the heat loss per foot in length, and the outside temperature is 100 degrees Fahrenheit. So what they do is they graphically represent this particular problem, and they give you all of the knowns here towards the bottom. Okay, so figure 5 just goes with the problem. So the equation that you need to use is Q divided by L is equal to 2 pi T in minus T out divided by the natural log of R over 2. I'm sorry, R sub 2, R1 over KS plus the natural log of R3, R2 over KA. And then they plug in and solve. So 2 pi times 550 minus 100 divided by the natural log of 6 over 5 divided by 12.5 plus the natural log of 9 over 6 divided by 0.14 equals 971 BTU per hour foot. So take your time and fill out the summary table for this particular chapter. Make sure you notate any equations. Please don't put all of the steps when the equations are derived, but put final equations that were used. So this chapter, we're going to talk about convection heat transfer. And this is heat transfer by motion and mixing of molecules of a liquid or a gas. And that is called convection. And the enabling objective is given the formula for heat transfer and the operating conditions of the system, calculate the rate of heat transfer by convection. So convection is the transfer of heat by motion of mixing of macroscopic portions of a fluid, that is the flow of a fluid past a solid boundary. So the term natural convection is used if this motion and mixing is caused by density variations resulting from the temperature differences within the fluid. The term forced convection is used if this motion and mixing is caused by an outside force such as a pump. And the transfer of heat from hot water radiator to a room is an example of heat transfer by natural convection. The transfer of heat from the surface of a heat exchanger to the bulk of the fluid being pumped through the heat exchanger is an example of forced convection. So heat transfer by convection is more difficult to analyze than heat transfer by conduction because no single property of heat transfer medium, such as thermal conductivity, can be defined to describe this mechanism. So heat transfer by convection varies from situation to situation upon the fluid flow conditions, and it is frequently coupled with the mode that the fluid flows. So in practice, analysis of heat transfer by convection is treated empirically, or it is treated as something that is directly observed. Convection heat transfer is treated empirically because factors that affect the stagnant film thickness are fluid velocity, fluid viscosity, heat flux, surface roughness, and the type of flow, whether it is single phase flow or two-phase flow. So convection involves the transfer of heat between a surface at a given temperature and a fluid at the bulk temperature. The exact definition of bulk temperature varies depending on the details of the situation. For a flow adjacent to a hot or cold surface, TB is the temperature of the fluid far from the surface. And for boiling condensation, TB is the saturation temperature of the fluid. And for flow in a pipe, TB is the average temperature measured at a particular cross section of the pipe. So the basic relationship for heat transfer by convection has the same form as that of heat transfer by conduction. So Q is equal to HA delta T, where Q is the rate of heat transfer, and that is in BTU per hour. H is the convective heat transfer coefficient, which is in BTU per hour foot squared degree Fahrenheit. A is the surface area, that's in foot squared. And delta T is that temperature difference in degrees Fahrenheit. So the convective heat transfer coefficient H is dependent upon the physical properties of the liquid and the physical situation. Okay. And so typically the convective heat transfer coefficient for laminar flow is relatively low compared to the convective heat transfer coefficient for turbulent flow. And this is due to turbulent flow having a thinner stagnant fluid film layer on the heat transfer surface. So values of H have been measured and tabulated, so they are constants for the commonly encountered fluids in flow situations occurring in heat transfer by convection. So they asked the question, a 22-foot insulated steam line crosses a room. The outer diameter of the steam line is 18 inches and the outer surface temperature is 280 degrees Fahrenheit. The convective heat transfer and the coefficient for the air is 18 BTU hour foot squared degree Fahrenheit. I'm sorry, BTU per hour foot squared degree Fahrenheit. Calculate the heat transfer rate from the pipe into the room at a temperature of 72 degrees Fahrenheit. So they use the equation for this problem. Q is equal to HA delta T. They substitute in for A, so Q is equal to H 2 pi RL delta T. And that is the equation that they use. So 18 BTU per hour foot squared degree Fahrenheit times 2, and of course pi is 3.14 times 0.75 feet times 22 feet. And all of this is times that temperature difference, which is 280 degrees Fahrenheit minus 72. So they wind up with a Q equal to 3.88 times 10 to the 5th BTU per hour. So many applications involving convective heat transfer take place within pipes, tubes, and some cylindrical device. In such circumstances, the surface area of heat transfer, normally given in the convection equation, Q is equal to HA delta T, varies as heat passes through the cylinder. In addition, the temperature difference existing between the inside and outside of the pipe, as well as the temperature difference along the pipe, necessitates the use of some average temperature value in order to analyze the problem. And the average temperature difference is called the log mean temperature difference, which was, aforementioned in the previous chapter, which was mentioned in the previous chapter. So it is a temperature difference at one end of the heat exchanger minus the temperature difference at the other end of the heat exchanger, divided by the natural logarithm of the ratio of these two temperature differences. The above definition of LMTD involves two important assumptions. One, the fluid specific heats don't vary significantly with temperature. And two, the convection heat transfer coefficients are relatively constant through the heat exchanger. So the overall heat transfer coefficient, many of these heat transfer processes encountered in nuclear facilities involve a combination of both conduction and convection. For example, heat transfer in the steam generator involves convection from a bulk of a reactor coolant to the steam generator inner tube surface, and conduction through a tube wall, and then convection from the outer tube surface to a secondary side fluid. So in cases of combined heat transfer for a heat exchanger, there are two values for H. There is the convective heat transfer coefficient for the fluid film inside the tubes, and then there's the convective heat transfer coefficient for the fluid film outside the tubes. And thermal conductivity, K, and thickness, delta X, of the tube wall are also accounted for. An additional term, we talked about internal energy, U, called the overall heat transfer coefficient, must be used instead. It is common practice to relate the total heat transfer Q to the cross-sectional area for heat transfer A and the overall heat transfer coefficient U. The relationship of the overall heat transfer coefficient to the individual conduction and convection terms is shown in Figure 6. Look at those. So recalling equation 2.3, Q is equal to U A delta T, where U is defined in Figure 6. An example of the concept applied to cylindrical geometry is illustrated in Figure 6, Figure 7, which shows a typical combined heat transfer situation. And so using the figure representing flow of a pipe, heat transfer by convection occurs between temperatures T1 and T2. Heat transfer by conduction occurs between temperatures T2 and T3, and heat transfer occurs by convection between temperatures T3 and T4. Thus, there are three processes involved, and each has a coefficient, a cross-sectional area for heat transfer, and a temperature difference. And so the basic relationships of these three processes can be expressed using Q is equal to H1A1 times T1 minus T2. Q is equal to K over delta R, A sub LM times T2 minus T3. And then Q is equal to H squared, is equal to H2A2 times T3 minus T4. And delta T can be expressed as a sum of delta T of the three individual processes. So delta T is T1 minus T2 plus T2 minus T3 plus T3 minus T4. And if the basic relationship of each process is solved for its associated temperature difference, substituted into the delta T equation above, the relationship is delta T is equal to Q times 1 over H1A1 plus delta R over K A sub LM plus 1 over H sub 2 A2. And this relationship is modified by selecting the reference cross-sectional area. So delta T is equal to Q over A, and then you multiply that by A divided by H1A1, delta RA divided by K over AL sub ALM plus A divided by H2A2. So then they're doing some more derivation steps, okay? So you're solving for Q, and it results in this equation. Q is equal to U A delta T. So here's some more substitution. So Q is equal to 1 over A0 H1 divided by H1 A1 plus delta R A0 over K A L M plus A0 over H2 A2. All of that times A0 is delta T0. Where U equals, so this is your final. Where U is equal to 1 over A divided by H1A1 plus delta RA divided by KALM plus A divided by H2A2. So equation 210 for the overall heat transfer coefficient in cylindrical geometry is relatively difficult to work with, which I would agree. The equation can be simplified without you losing much accuracy if the tube that is being analyzed is thin-walled and the tube wall thickness is small compared to the tube wall diameter. So for a thin-wall tube, the inner surface area A1 and the outer surface area A2 and the log of the surface area A sub LM are very close to being equal. So assuming that A1, A2, A sub LM are equal to each other, and also the A sub 0 allows us to cancel out the area terms in the denominator of this equation. So we have to make a very large assumption. Then you wind up with this equation for developed for flat plate heat, which is U0 is equal to 1 over H1 over delta R over K plus 1 over H sub 2. So the convection heat transfer process is strongly dependent upon the properties of the fluid. Correspondingly, the convective heat transfer coefficient and the overall coefficient U0 and the other fluid properties may vary substantially for a fluid if it experiences large temperature change during its path. The convective through the convective heat transfer device. And this is especially true if the fluid's properties are strongly temperature dependent. Under such circumstances, the temperature at which the properties are looked up must be some type of average value rather than using either the inlet or the outer temperature value. So for internal flow, the bulk average or the average value of temperature is obtained analytically through the use of conservation of energy. So for external flow, the average film temperature is normally calculated, which is an average of free stream temperature and solid surface temperature. And in any case, an average value temperature is used to obtain fluid properties to be used in the heat transfer problem. So the following example shows the use of such principles by solving a convective heat transfer problem in which bulk temperature is calculated. So a flat wall is exposed to the environment. The wall is covered with a layer of insulation that's 1 inch thick, whose thermal conductivity is 0.8 BTU per hour foot degree Fahrenheit. And the temperature of the wall on the inside of the insulation is 600 degrees Fahrenheit. And the wall loses heat to the environment by convection on the surface of the insulation. The average value of the convection heat transfer coefficient on the insulation surface is 950 BTU per hour foot square degree Fahrenheit. So they're asking to calculate the bulk temperature of the environment, the TB, if the outer surface of the insulation does not exceed 105 degrees Fahrenheit. So they use the equation, they use the equation where you find the heat flux through the insulation. So Q is equal to Ka times delta T over delta X. Q over A is equal to 0.8 BTU per hour foot degree Fahrenheit. And then of course they subtract the temperatures, 600 minus 105, and they divide it by this conversion factor where 1 inch is 1 inch times 1 foot over 12 inches. So they also, for part B, you need to find the bulk temperature for the environment. So Q is equal to HA times T insulation minus TB. T insulation minus TB is equal to Q over HA. TB, which is the bulk temperature that you're looking for, is equal to T insulation minus Q over H. So TB is 105 times 4,752 BTU per hour foot squared divided by 950 BTU hour foot squared degrees Fahrenheit. And so the bulk temperature is 100 degrees Fahrenheit. So take your time and put the, not all the derivations, but the formulas or the equations that were used on your summary sheet. We will finish the rest of